My name's Luke. I'm a compiler engineer at Igalia, and this will be talking about some work that myself and Michael Maitland at Sci5 carried out to do with the RISC-V VL optimizer and how we kind of extended it. And yeah, this talk is kind of like it's in kind of a meandering story kind of format, so please bear with me. But I'll start with the motivation for this work, and it begins with this feature that we've wanted in the RISC-V backend for quite some time. And I should say it's really in the middle end, but we want to perform EVL tail folding. And what this is, it's folding the tail of the loop that the loop vectorizer will emit into the body of it, so we just have one vectorized loop. The reason why the loop vectorizer emits two loops in the first place is because vector ICEs, they'll have vector instructions, right? And they'll process like a fixed number of elements each time, like say 4 elements. We call that the vectorization factor. And if your trip count is an awkward number that's not exactly divisible by the vectorization factor, you need this scalar loop at the end to kind of mop up those leftover elements. The idea behind tail folding is that some vector ICEs, like RISC-V, have features that allow you to mask off lanes in the vector instructions. And with that, you can then get rid of the scalar loop at the end and just do everything in the vector loop by masking off the unneeded lanes in the last iteration. So RX64 has this enabled by default for SVE, from what I understand, but they do it via mask registers. What's kind of unique to RISC-V is that it's got a dedicated scalar register called the vector length register. That's this VL that we'll hear about tons. And it means that we don't need to compute a mask. And support for this was landed last year. This was like a really long time coming patch. Like this patch started off in like Fabricator and then moved over to GitHub. But it's been a tremendous amount of work, and thanks everyone for making it happen. But it's enabled behind a flag for now. There's some significant code gen changes involved with this that we still kind of need to evaluate and hammer out. So I guess the goal that I was trying to pursue was how can we enable this by default? What needs to be done? And I think the best place for kind of evaluating whether or not a feature is ready is by seeing how it runs on some real-world pieces of code. So LLVM test suite is great for this. Not only does it have a bunch of benchmarks and tests inside it, but you can also plug in things like spec CPU and stuff into it. It's a really useful harness for evaluating these types of changes. So the first thing I did was basically just, give it a build. I configured, I then pointed it to my client compiler and passed in the right flags. And then ran it on lit and saw that, okay, well, there's miscompile, so we can't enable it by default yet. These need to be ironed out. And unfortunately, this is a miscompile in like a new feature. So I'm a pretty lazy developer, and usually whenever I see a miscompile, I just like write a script and chuck it into git bisect. But you can't do that here because this miscompile has been here since day one, since that patch landed. So really the only technique that you have is to just stare at the binaries and try and figure out what went wrong. But this was a miscompile in GCC. There's like, what is that, 90,000 deletions, 90,000 insertions? Like, there's no way I'm going to be able to figure out what that is. But I stumbled across this really useful script that has been sitting around for quite some time. I don't know, maybe other people are more familiar with it, this RSP bisect.py script. What it lets you do is it lets you take a known good build and a known bad build, but these can be like different configurations. So in our case, it's a build with EVL tail folding and a build without. And yeah, you give it like a script to recreate the miscompile, and what it will do is that it will kind of bisect between the object files of the good binary and the bad binary until eventually it narrows it down to like a minimal set, I guess, of binaries that are known to cause the miscompile. And from that, I was able to figure out, okay, well, there's one object file that has some changes in it. And from that, I was able to actually dig in a bit deeper and figure out the cause of the miscompile by reducing the surface area. So that was a very useful script. And yeah, we were able to fix the miscompiles. So that was fantastic. And we were able to then start doing some performance testing. So we ran it on spec using LNT, and we saw some really nice gains. And we were really tempted to enable it by default at this point, but we have to do our due diligence. We should probably also actually look at the generated code to make sure that nothing else is going wrong, right? So there may be regressions hidden behind that, 16% improvement that just are kind of covered up. But again, LLVM test suite has a very useful set of tools and scripts, and it has this script tdiff.py, which, I don't know, Many of you probably also use this on a day-to-day basis. I use this all the time, but it's great for comparing the kind of differences between two builds. So I stuck that in just to see what the difference was, and I noticed, okay, well, there are actually some regressions lying in the code gen here whenever we enable EVL tail folding. So this is an example here about how we're not able to match a widening multiply. And what I did was I looked at the LLVM IR to see what exactly was the root cause of this. And here's another useful tool, LLVM extract. If you're looking at lots and lots of LLVM IR, LLVM extract can just pick it out from the function that you know to be suspicious. But yeah, here's the difference. The difference is that we no longer have a multiply instruction. The loop vectorizer with EVL tail folding emitted this llvm.vp.mul intrinsic with a bunch of scary looking arguments, but it's not too bad. These are VP intrinsics. They're vector predication intrinsics, and they're how the loop vectorizer controls the masking and predication for EVL tail folding and for just other types of tail folding within the loop vectorizer. The annoying thing about these intrinsics, though, is that they're opaque to a lot of optimizations, to a lot of combines, and you need to make sure you have the correct patterns through them inside your own backend, which was the root cause here. In this case, the RISC-V backend wasn't, it didn't have the patterns for this widening multiply at the VP intrinsic level. So the loop vectorizer needs to emit these VP intrinsics for trapping instructions, so your loads and stores, because we need to make sure that we're not actually executing on those lanes. But you might be thinking, well, why do we need to do it for the instructions that don't trap? Is there any harm in just calculating that multiply for a disabled lane? And it turns out that on some microarchitectures for RISC-V, we do want to reduce the VL for even instructions that we aren't going to trap, because they can optimize that and carry out less cycles if that VL is reduced. This screenshot is a screenshot from the vector predication roadmap, which is attached to RFC, and it kind of had this like 3-stage plan. And the final stage of the plan was to lift every single combine to work on VP intrinsics, at ins combine, at ins simplify, DAG combine. That's a lot of work, right? So I was looking at that thinking, okay, is this a dead end? Are we just stuck with subpar code generation? But that's where Michael Maitland kind of came in. And he was also looking at EVL tail folding at Sci5, but he was looking at a different problem. The problem that he was seeing was that there's no VP intrinsic for the get element pointer instruction. So that meant for any kind of loop that was vectorized, that was like a gather, we were calculating addresses unnecessarily, and we weren't reducing the VL in those lanes. We were doing unnecessary work. We don't have a get element pointer VP instruction because get element pointer is just like a weird instruction in general. It's like variadic and stuff, and like I think it's going away. But in any case, we need to find a way to, well, Michael wanted to find a way to reduce the VL in this case. So he upstreamed this patch, the RISC-V VL optimizer, which is the title of this talk. And what it does is that it's like the loop vectorizer emitting VP intrinsics. It also reduces the VL of instructions, but specifically, it does it in the RISC-V backend. And I think it's quite elegant the way it works. It's basically just a loop from the bottom of a basic block all the way up, kind of like in a reverse post-order fashion. For every instruction, it'll just look at its users, and then it'll take the maximum VL that is demanded by each of its users, and then reduce its VL if it's possible. And then this repeats, but just the way it works is that it kind of like bubbles up. And so it's able to reduce the VL of entire trees, and like, a pretty simple algorithm, which is fantastic. For the RISC-V folks, if anyone's curious, we do have to take into account V-type here, like EEW and EMOL, and that's where the bulk of the logic of this pass lies. So I'm not going to divulge into it too much because that's like a whole other separate talk. But in any case, yeah, the key thing about this pass is that it sat at the machine instruction level. And whilst it also reduces the VL in the same way that VP intrinsics reduce the VL, the key thing is that because it does it at the MIR level, it's able to reduce both regular LLVM IR and VP intrinsics, because they both get lowered into the same machine instructions at the end of the day. And so that meant that the loop vectorizer, whenever that pass landed, we didn't have to emit VP intrinsics anymore. We could just emit regular LLVM IR instructions, and we got the best of both worlds. We got the good cogen, and we also got reduced VL. And like we basically got that for free with that pass, which is great. So again, we started thinking, okay, can we enable EVL tail folding on by default now? But again, we have to go check with LLVM test suite, find regressions, and this is not so much as a regression as much as it is like a missed opportunity here. But the VL optimizer was great at optimizing the VL in most cases, but there were some cases like this where we weren't, catching these final cases. These cases more or less revolved around phi nodes. So here's an example here where the VL optimizer wasn't able to previously handle, and this is kind of where we began extending it. So in this kind of example here, we have a phi node, and its users are the A and B kind of like values. We should be able to reduce the VL of A and B to 2 because ultimately they're only used by a store, like this root instruction, which only has a VL of 2, right? We should be able to reduce this all the way. But these store instructions and these add instructions that you were seeing in the previous slides, these are RISC-V specific machine instructions. They're not target independent, and they have the VL operands. The phi instruction is a generic machine instruction, so it doesn't have a VL operand. So whenever the VL optimizer kind of encounters this phi instruction, it's not able to reduce it any further. So the first thing that we addressed and the first thing that we extended was that we split this optimizer into 2 parts. We created a map which mapped instructions to the VL that they demand, and we then did the analysis. It's like the same thing where we're just computing the maximum VL demanded from its users. And then in a separate step, we actually did the mutation, just looping over the instructions again and looking up in that map. And that meant in this case, whenever we reached the phi node, we were able to reduce the phi node or the demanded VL in its demanded map. And then we could propagate that up to A and B, which meant that we could then, in a separate step, do the actual mutation. So we're no longer doing it in situ. The second example that we saw was this kind of like phi recurrence. Right off the bat, we knew that this kind of bottom to top single pass approach wasn't going to work because now the A phi node uses B, which is beneath it, so we're going to have to switch to like a work list approach where we append instructions to it, and then we, inside the loop, we pop it off, and then we append the inputs to that instruction back onto the work list. And what's important here is that we also need to check that the demanded VL of that instruction actually changed. And only then, if it changed, do we append its operands onto the work list, because we want to iterate to a fixed point here, otherwise we'll just end up with infinite loops. So if we go ahead and try this out, we're hoping that we can reduce the demanded VL of B to 2, but it still doesn't work this way. It's because this phi node still has a demanded VL of VL max, right? And it's one of the users of B. So we needed to go ahead and fix this, and what we had to fix was the fact that we're too conservative in our initial demanded map. We had to relax this. So now instead of initializing the demanded VL map to the initial VL operand of every instruction, we're going to go ahead and assume nothing is demanded. So that's obviously not correct. If the store is going to demand that some elements are computed, but we'll just run with it for now and assume that nothing is demanded. And then, instead of every instruction computing its own final demanded VL, we'll have each instruction work out what it requires and then propagate that up to its inputs. So in this case, we'll visit the store and then say, hey, I need a VL of 2. I need 2 elements. It'll propagate that up to the demanded VL of its input B, and then B will do the same in turn, propagate that up to the phi, and then because B is a input to the phi node as well, it'll go back around. But here, because nothing changed ultimately, we've kind of reached a stable fixed point, the algorithm will terminate. So that's great. We were kind of able to handle these nice general cases. And of course, yeah, we have to go ahead and do the actual mutation. And about this point, we kind of realized, this is kind of smelling kind of like a compiler theory problem. So we took a step back and kind of took stock of what we had. We had some sort of notion of like a state. That's our demanded map. That maps, instructions to some sort of demanded VL. We also had this notion of an initial state where everything is initialized to 0. And we also had this function in the middle of this loop that moves from one state to another, And that's when the penny finally dropped that, oh, hey, this is just data flow analysis that we've ended up making. We have our transfer function, we have our notion of a least element or a bottom, and our state, of course. Some interesting things to note about this data flow analysis is that it's a sparse data flow analysis, it's not a dense one. We're not computing the state at basic block boundaries, and we're not computing at individual points in the program. We're only using the USDEF chain, and yeah, that's represented by what we store in the state. And it's an optimistic data flow analysis because some data flow analyses, they start off conservative, and then at any point in the algorithm they can terminate. We have to run this kind of like while loop to completion, otherwise it's not correct. So that's the meaning of the term optimistic. And yeah, the state forms a semi-lattice. The way to think about this is like a map of every possible state that the analysis could be in. It'll start off at the bottom, and then as it goes through the instructions and see what's demanded, it'll kind of like float all the way up to the top until everything is demanded in the worst case scenario. The ordering, or the partial order, whatever it's called in maths land, it's defined as one state being ordered above another state if the VL for all those definitions are greater than that other state. But with all this theory anyway, we can use it to actually answer some pretty useful questions like, okay, we have this work list and we're popping off it and we're appending things back onto it. Do we know it's ever going to terminate? That's like a very useful property to know. And we can use the semi-lattice that we've defined to actually prove this. Specifically, well, to look at it kind of the way I view it, we start off at the bottom every time with nothing is demanded. That yellow kind of bit in the function here, that's our transfer function. Whenever we read an instruction and propagate the demanded VL, we're moving up the lattice. And the key thing to note is that we will only ever move up the lattice, we will never move down. So we can keep on going until we compute what's demanded for more and more elements, but we will never move down the lattice, so we will never end up in a cycle. We will always either reach a stable point, at which point the algorithm will terminate, or we will go all the way up to the top, at which point everything's demanded and we can't do anything else. Here's kind of like the more kind of formal reasoning about it. The semi-lattice is finite because the height of it, i.e. the longest chain from the bottom to the top, it's determined by the number of definitions in the program and the number of unique possible values that were used for the VL operands, which is finite. And the transfer function is monotonic, because if you look at that definition at the bottom, yeah, it's either going to be the previous demanded VL or the maximum of the previous demanded VL and something else. So no matter how many times you apply the transfer function, it will never give you a demanded VL that's less. And so it's monotonic with respect to that relation. And yeah, I guess that kind of brings us to where we got with extending this RISC-V VL optimizer pass. There's still some patches that need to be upstreamed, and we still need to kind of properly evaluate the whole thing. But yeah, this is kind of a funny story, but up until today, I had left this kind of last bullet point as like a piece of future work where, I thought it would be really cool to, not do this hand-wavy maths and actually formally verify it. So I gave it a stab in lean. Turns out I'm not really a mathematician. I didn't really get anywhere. Left it as, yeah, future work. But earlier today, I attended a talk by Siddharth Bhatt on the, formally verifying, I think it was, yeah, ins-combined people optimizations. It was a great talk. If you haven't seen it, I'd highly recommend checking out the recording if it's available. But I saw that talk at 11 o'clock, bumped into him in the hallway at 12, got talking to him. He seemed quite interested in this problem. By 3 p.m., he had sent me actually a mechanized proof of this all. So I guess, yeah, thank you, Siddharth. You've, yeah, kind of done that last bullet point there, so it's no longer really future work. But yeah, we can indeed verify that this algorithm does terminate. And so hopefully RISC-V VL optimizer will never be the cause of an infinite loop. So again, thank you so much, Siddharth Bhatt. And yeah, I don't know how you did so quickly. It's like 500 lines of lean, and I don't really understand much of it, but thank you. And yeah, thanks to Michael Maitland as well, who couldn't be here, who did all the hard work in upstreaming this. And yeah, I'm happy to answer any questions. Thank you.